Hey guys, and welcome back to another episode of Everything Science. On today's episode, we'll be discussing the end of a decades-long plutonium shortage and the ancient lakes that may have hidden just below the Martian surface. Don't forget to like and subscribe, and let's jump in. Good news for all you lovers of space exploration. It appears the US's decades-long plutonium-238 shortage is finally coming to an end. For those of you who don't know, plutonium-238 is a crucial component for all long-term and deep space missions, but national production was halted in 1988, and by 2015, a national shortage was looming on the horizon. Like most of our knowledge of nuclear physics, the discovery of plutonium-238 came as a direct result of the Cold War. In December of 1940, renowned chemist and Nobel laureate Glenn Seaborg bombarded uranium-238 with deuterium, hydrogen with a neutron attached, creating plutonium-238. These channels do a really good job at explaining the physics behind these reactions, but in simple terms, you can think of atoms like a waiter holding plates. If the waiter's holding one plate, they're fine. 2, 3, they're still fine. But you can imagine if you give them more and more plates, eventually the system will become unstable and everything will come crashing down. The atom works in a similar way. If you take a stable atom and keep adding more and more neutrons to the system, eventually it will become unstable and decay into a new element. While this might sound confusing for any of you that know that the difference between two elements is the number of protons they have, not the number of neutrons, you need to keep in mind that neutrons can decay into a proton, an electron, and an antineutrino. So in this way, bombarding an atom with neutrons can actually add protons to the system. Plutonium-238 is created by bombarding uranium with deuterium, which then decays into neptunium and then again into plutonium. The key here is that plutonium-238 is also unstable, eventually decaying into lead. But this process takes hundreds of years and gives off energy as it happens, and it's this energy that NASA uses to power its missions far from home. But a lot of isotopes give off energy from nuclear decay. Heck, even a banana gives off nuclear energy as the potassium within it decays. So why aren't we powering our deep space probes by banana fuel? What is big nuclear hiding? Well, while there are almost 3,000 nuclear isotopes, most aren't very useful. According to the National Research Council, of the 2,900 known nuclear isotopes, plutonium-238 is the only practical option for fueling deep space missions. Among the reasons for this is plutonium-238's remarkable half-life of 87.7 years, which allows it to be used for well over a century while still providing enough heat to keep probes and rovers in the far reaches of our solar system working. While the gallium arsenide solar cells that have powered spacecraft like Juno work well for explorations of the inner planets, they become seriously hampered once reaching Jupiter and beyond. While the traditional solar cells that you might find on your roof at home can top out at around 21% efficiency, the gallium arsenide solar cells found on spacecraft can reach up to 37% efficiency. Because of Juno's extreme distance from the sun, it took 3 solar arrays totaling nearly 19,000 solar cells spread across 50 square meters of array to power the craft on its way around Jupiter. Meanwhile, the same amount of power can be generated by just 3 nuclear reactors like the ones carried by Cassini. If you're interested in hearing more about these missions, make sure you leave a comment down below and hit subscribe so you don't miss out. The problem here is that as you pass Jupiter, even the top of the line solar panels just can't keep up. By the time you reach Jupiter's orbit, there's only about 4% as much light energy as experienced in Earth's orbit. By the time you reach Saturn, it's less than 1%. So you can see why any deep space missions or rovers on dusty worlds like Mars would need an alternate form of power. But like many aspects of the space race, plutonium-238 was primarily seen as a tool of the Cold War, and as the Soviet Union began to pose less of a threat, domestic production was slowed and eventually halted in 1988. Forcing NASA to use dwindling reserves ever since. In recent years, the annual US production across the entire United States was a whopping 50 grams, and the national stockpile was down to 35 kilograms. Keep in mind that individual rovers like the Mars 2020 rover need 5 kilograms each. So by 2015, there appeared to only be enough left to power NASA missions through the 2020s. But hope is on the horizons. Thanks to recent developments out of the Oak Ridge National Lab, a key step for the production of plutonium-238 has been automated, octupling national production and moving us closer to NASA's goal of making 1.5 kilograms per year by 2025. With increased production, future missions like Cassini and the Mars 2020 rover can be built knowing they'll have fuel sources that will last well past their launch dates. And this fuel will be critical for the next generation of space probes and rovers like the Mars 2020 rover that seeks to discover if life ever existed on the surface of Mars. but we might not have to wait so long to find out. Mars Express, the European Space Agency's first planetary mission, recently discovered the first evidence of a planet-wide groundwater system on Mars. This discovery comes to us from the same probe that just last year detected liquid water below the planet's south pole. Mars Express was originally launched in 2003 and has been collecting high-resolution imaging and meteorological data of the Martian surface and subsurface ever since. Recently, its measurements found the first geological evidence of a planet-wide system of underground interconnected lakes just below the red planet's surface, some of which may contain minerals crucial for life. Nowadays, we can see steep valleys and canyons that must have been carved by flowing water. This tells us that sometime over Mars' 4.6 billion year history, liquid water must have existed on its surface. This new study reveals the extent and scale of underground water on ancient Mars. The researchers here explored deep craters in the northern hemisphere of Mars and found features like deep cuts etched into crater walls and fan-shaped deposits of sediment that could only have been formed in the presence of water. Many of these craters contain multiple features at different heights, indicating that they once contained pools of water that raised and receded over time. Researchers believe these craters tapped into an underground system of lakes spread across the planet, similar to how water tables work on Earth, and they existed for nearly 1 billion years. But I know what you're thinking. Did anything swim around the bottom of those craters? The team found certain minerals like carbonates and silicates in the craters that are thought to be the prerequisites of life here on Earth. With liquid water, the ingredients for life, and 1 billion years for it to develop, researchers believe that these basins are some of the most likely places to discover alien life on our neighbor planet. But the only way to find out for sure would be to send a probe to get its gears dirty in one of these craters. But since they're almost half a kilometer deep and have steep walls with irregular topography, it would be very difficult for a rover to traverse, and so NASA has no plans of going digging in them anytime soon. But with more rovers on the horizon, like the European Space Agency's Rosalind Franklin and NASA's Mars 2020 rover searching the surface of Mars for signs of life, it might not be long before we have something to report. Well, that's it for today on Everything Science. If you like this content and are interested in seeing more, don't forget to like, comment, and subscribe to stay up to date on everything science.